Okay, and we're going to start off with looking at what the most basic building block of a computer program is, and that's numbers. In fact, what we'll find is that numbers are the basis of almost everything in a computer program. It's numbers that we use internally in the computer to represent letters of the alphabet, punctuation symbols, etc. And ultimately, one of the tasks that we'll have in biomedical sciences is being able to take biological and medical data and figuring out how to represent that data as numbers so that we can do computation on it and statistical inferences, machine learning, etc. So we're going to start off by reviewing basic concepts of numbers, and you can read over the notebook in more detail. Wanted to emphasize that the kinds of numbers we have result from the different purposes that were at hand as humans invented numbers. And so we have numbers discrete numbers that arise from counting things, and these are going to be our integers, 1, 2, 3, 4. And when we have numbers that arise from measuring things, whether that's a weight, a height, etc., and these are our real numbers. And the fact that these are two different processes result in numbers that can be related to one another isn't something that was kind of mathematically finalized until into the 19th century. The first set of numbers that we might think of are our counting numbers, or 1, 2, 3, 4. And these are referred to as the natural numbers. Sometimes the natural numbers include 0, but there are not, so they're either our positive or our non-negative integers. And we can do a lot with natural numbers. We can add them, we can subtract them, we can multiply them. However, depending on the process that we do, we may not end up with a natural number in our answer. So if I take 3 minus 5, both of them are natural numbers, but I end up with a negative 2, which is not a natural number. And similarly, I can pick two natural numbers to divide, and I can, depending on my choices, I may not have a natural number in the end. The most important set from our perspective of these counting numbers are integers. And so integers include our positive numbers, discrete numbers, 0, and our negative discrete numbers. And we denote integers, or the set of all integers, with this fancy z from the German Zahlen, meaning number. Rational numbers are numbers that are formed by the ratio of two integers, and that's going to be denoted by this fancy q. And now we get into the real numbers. So the real numbers include all the numbers that we've talked about, the natural numbers. So the natural numbers are a subset of the integers. The integers are a subset of the rational numbers. So real numbers introduce a completely different kind of family of numbers. And so when Pythagoras had all his numbers, he meant integers, rational numbers. But it's been known since the ancient Greeks that there were numbers that are called irrational numbers. And these are numbers that cannot be expressed as the ratio of two integers. Famous irrational number is the square root of 2, and here I provide a proof that why the square root of 2 is irrational. Pi would be another one. Whereas we think of integers as counting, we're going to think of real numbers as distance along a line. So this is our number line. And you see that we can place our integers on this number line, but then we have other numbers like the square root of 2, e, or pi that are not rational numbers that nonetheless can be viewed as some distance, either positive or negative distance, from the origin. Now, a set of numbers that you may not be as familiar with are the complex numbers. So complex numbers were introduced to help us deal with particular algebraic problems. So we're familiar with the equation x squared equals 9, and so we would recognize that x is equal to 3 or negative 3. If we square 3 or negative 3, we get the number 9. But what about an equation like x squared equals negative 1? So a real number multiplied by itself cannot give us a negative number. And so mathematicians introduced the concept of a complex number. And a complex number consists of a real and what's called an imaginary part. And this imaginary, and it's the sum of these two numbers, and I is taken to be this special number that is the square root of negative 1. So when I take I times I get negative 1. Well, just as we view the real numbers as a distance along a line, we can view a complex number as a position in a plane, where the real part is its distance along this x-axis, and the imaginary part is its distance along the y-axis. So here we'd have the point 3 plus 2i. We come over 3 points on our real axis and up 2 on our imaginary axis, and this becomes a complex number. And complex numbers are very important in describing a variety of physical processes. If you're involved with imaging like I am, if you take a CT or an MR image, these images are all generated using complex numbers. And there's rules of arithmetic that are defined for complex numbers. So how do we add them? How do we multiply them? How do we divide them? Complex numbers are really valuable in that they're complete. There's no polynomial equation that we can come up with that does not have a complex number as a root. So it was easy to create a polynomial number equation that did not have a real solution. So they're nice from that mathematical point of view, and they are also important from representing various physical processes that we may be interested in. With computers, so the integers, there's no largest integer. We can always generate another integer that's larger by adding 1. And similarly with real numbers and complex numbers, there are an infinite number of them. We cannot, however, represent infinitely large numbers in our computers, because the way we represent numbers in our computer is with a transistor, a piece of electronic device that is either kind of a 0 or a 1. And so because we only have a finite number of transistors in our computer, there's only a finite number, finite sized numbers that we can represent in our computers. And so every computer programming language like Python is going to have some limit into what it can represent. And so Python has a concept of a max size. So if I import this package sys and I print what the sys.max size is, this will tell me what the maximum integer that I can represent on my computer is. And since most of our computers these days are 64 bits, and because integers are positive or negative, I have 63 bits that I can use to represent my number. One of my 64 bits has to be used to represent whether it's a positive or negative sign. And so what I have is 2 to the 63rd, and that's the number of numbers that I can represent. And of course, I'm also representing 0. So if I subtract 1 from that, then that's how I get the largest number that I can represent. There's similar issues with floating point numbers. Floating point numbers are very different in how they are represented in the computer. They're represented approximately. And so when I do mathematics with integers, I get exact results. When I do mathematics with floating point numbers, I get approximate results. And how accurate that approximation is depends on my computer architecture. But just as there's information about what the largest integer that I can represent, Python also has information about what the largest floating point number or real number I can represent, and what the accuracy of that number is. So epsilon is the smallest difference that I can detect between two numbers, and my maximum float and my minimum float are the largest real number and smallest real number that I can represent. And so here basically we have 10 to the 308th is my largest number, and 10 to the negative 308th is the smallest. And the smallest difference I can accurately compute between two numbers is on the order of 10 to the negative 16th. There are other kinds of numbers that we might be interested in. And here are some links to, well, this is not really different kinds of numbers, but this is a link to a discussion of different kinds of measurements and what kinds of mathematics are meaningful on those different kinds of measurements. There are other kinds of numbers that maybe a mathematician wouldn't consider as a number that Python can deal with. So for instance, Python has a concept of a decimal number where I can fix the number of decimal points that number can have. And that would be useful, say, for dealing with currency, where maybe if we're dealing with US dollars, our smallest unit of currency is a penny, and so we may want to fix our number to have at the most 2 decimal points. But that's our basic review of different families of numbers from a mathematical point of view and a basic computational representation. And our next one we will deal with has how do we deal with these directly in Python.